So this can be done in space, this can be done in time. So in this particular problem, which we shall show now, we are marching in time. So we know the present solution. Knowing the present solution, we shall predict the future solution. Okay. So the values of the unknown is the temperature in this particular equation. We shall predict the values of the unknown at different nodal points with future times. Okay. And then when we have discussed the differences between this implicit scheme and the explicit scheme, then we mentioned that in this equilibrium problem, we have to use only the implicit scheme. But when we are going for the marching problem, this marching problem after discretization, it can be solved by explicit. We can use explicit scheme for discretization, or we can use the implicit scheme for discretization. So this point I am repeating. Okay. So equilibrium problems, we have to discretize only by implicit scheme, but marching problems, we can discretize by using explicit scheme or by using the implicit scheme. So both are possible in case of marching problems. So in today's class, we shall show the discretization of marching problems using the explicit schemes. Okay. So one explicit scheme you already know, the FTCS, forward in time and central in space, that we have already discussed. So we shall show it, how to implement it, and then we shall show one part solution of one example problem, a simple problem. So that will give you some idea. Okay. So let us just share the material and continue the discussion. So students, can you see, is the screen readable? Can you read it? Can you read the text? Can you see it? Is the note?
Yes, sir.
Yes, sir.
Acha, okay. It is little light actually, the resolution. So okay, let us just continue. Let us just continue. Okay. So the differential equation, as I was telling, this is the parabolic partial differential equation in one dimension. So we have one unsteady term and we have one diffusion term. So this is the transient heat diffusion equation in terms of temperature. So here temperature is a function of both space and time in one dimension. This is the governing equation. Now we shall discretize this equation by the explicit scheme. This is also known as the simple explicit scheme or the FTCS scheme. Okay. So when we have the unsteady state equations, we have two indices. One is the index for the time level. Okay. So this index for the time level, this is denoted by the symbol small n, and the spatial index, the spatial coordinates or the nodal coordinates, they are denoted by the index small I. So I is the spatial coordinate and n is the indicator of the time level. Okay. So we are discretizing this time derivative at ith point at nth time level, and also the right hand side of this equation we are discretizing at one arbitrary node I at nth time instant or nth time level. Okay. So alpha is a constant, so the value of alpha will be same at all I at all n. So explicit scheme means, you know that when we discretize an equation by explicit scheme, we keep that in all equations there will be only one unknown. Okay. So this is like giving you a diagonal matrix we get. This gives you a diagonal matrix. We have discussed it already. So whenever we are using explicit scheme, it generates one unknown per equation, and all the equations, they are decoupled from the others. Okay. So if you want to solve the first equation, you need not depend on the second, third, or the remaining equations. You can easily solve first equation, or you can solve the unknown for any equation, because explicit scheme gives us a diagonal matrix. These things you know actually. Okay, we have discussed it already. So when you discretize by the FTCS scheme, so here n plus 1 is the unknown level, the unknown temperature, and this n is the known temperature. So in this equation, it is already discretized. So this is forward in time and this is central in space, that is FTCS. So when we are using FTCS, here we are getting at point I, okay. So in the left hand side, we are discretizing at ith point. So it is changing with respect to the time. So here the time level, index for the time level, it will change. Coordinate will not change. So it is Ti, Ti at the same point. So we are finding the difference in temperature at the same point, but at different time levels. So this is Tin plus 1 minus Tin, and this is the increment in time. In the right hand side, we are using central differencing scheme. So this is the expression for central differencing. Ti plus 1 minus 2Ti plus Ti minus 1 by delta x whole square. But we have the space, the time index. Now, since we are using explicit scheme, we have only one unknown at one time level, at one equation. Because of that, it must be n. So all the indices here, it is n, so that we have only one unknown per equation. So this is giving you the generic equation after simplification. So we are simplifying this. This is the algebraic equation. Okay. So this algebraic equation is having the compact form. This is the compact form of this generalized algebraic equation after discretization, where we have only one unknown. The terms with n plus 1, they are the unknown terms. The terms with n, they are the known terms. Okay. So unknown term is in the left hand side and known terms in the right hand side. Here we have the material property alpha, we have the time limit, means time scale, we have the space scale, means grid size in space and grid size in time. So their combination, we define it as a diffusion coefficient. So it is alpha delta t by delta x whole square. So this is alpha, this is d, the diffusion coefficient. So what is happening that this is the explicit formulation, the simple explicit formulation or the FTCS formulation for this heat diffusion equation in one dimension. So in the future classes, we shall discuss in two dimensions. It is very straightforward. Now, how will you calculate the temperature at different points with increasing time level? Okay. So to make this, to explain this, we are making two-dimensional representation. So it is actually one-dimensional problem, but we are just trying to explain it in a two-dimensional way. So along the x dimension, we have the spatial coordinates, and along the y-axis, we are putting the time coordinate. Okay. So the same grid, okay, we are plotting the grid here at different time levels. So these corresponding coordinates, they are not changing. Okay. So this is at nth level, this is at n plus 1th level, n plus 2th level, n plus 3th level. So time is increasing in the upward direction. Okay. Now at point I, you want to get the solution at n plus 1th level. At point I, you need the solution at n plus 1th level. So this is the unknown temperature. So this unknown temperature is here. So this is the point where we are trying to find out the solution. And this solution depends only on the known temperatures from the previous time level. So this is previous time level. Okay. So if you say this is current, then this is previous. Okay. So we are taking that n plus 1 is current, so n is previous. So all the values of temperature at I plus 1th node, ith node, I minus 1th node at the nth level of time. Okay. So they are giving you the solution at n plus 1th level. So by the dotted lines, we are showing the dependence. Okay. So once you find the temperature at this point at n plus 1th level, then you have to calculate for this point, you have to calculate for this point, and so on. After all the points on this n plus 1th level we have calculated, then we move to the next time level or n plus 2th level. So n plus 2th level solutions at point I, they depend on this n plus 1th level solutions. So the solutions that you have just calculated, they will be used to find out the temperature. So like that, it is actually it is not that the space is moving. Okay. So the meaning is that, the explanation is that it is not that the grid is moving. The same grid we are showing at different times, and you will keep on doing this calculation, simple calculation. There is no matrix calculation. Okay. So you will do simple calculations unless temperatures at all points at n plus 3th time level and n plus 2th time level, they become less. It means that temperature at this point and temperature at this point, at these two successive time levels, when their difference is less than 10 to the power minus 5 or 10 to the power minus 6, for example, then we say that we have achieved convergence, okay, and then we stop actually. Then we say that we have the correct solution. It means that in explicit scheme, when you are going for this with these calculations, you are continuously improving your solution. When you are increasing the time, you are actually improving the solutions. Okay, I shall show this example problem, then things will be very clear. Okay, so let us show one dimensional problem. So this is one rod. This rod is 1 meter long, and two boundaries, they are specified with temperature. So Dirichlet boundary conditions with 30 and 100 degrees centigrade, and there are 5 nodes on this bar, on this rod, and grid size will be accordingly zero point 0.2. Okay, so this is delta x. Okay, so we have 0.25. So this is delta x. So you have 4 delta x. So 4 into delta x is 1. So delta x is 0.25 meter. Now we have 5 nodal points. Node 1, node 2, 3, 4 and 5. Out of this, nodes 1 and 3, they are nodes 1 and 5, they are boundary nodes. So your unknown nodes are nodes 2, 3 and 4. So this formula, the generic formula, when you want to write, when you want to implement for this problem, particular problem, your I will vary from 2 to 4. So I will be 2, you get the solution at this point. Then I is 3, you get the solution at this point, and I is 4, you get the solution at this point at a certain time level, and then you have to improve this time level. Okay, so we have given the data that the rod is 1 meter long, and this thermal diffusivity alpha, this is 1 meter square per second. Okay, then we have given the time step size that you use delta t of 0.01. So use FTCS and try to find out these temperatures at these points. So this problem is not fully shown, but here we have made that the way it is done, your concept will be very much clear that how to use explicit formulation or simple calculation. Okay, so your first step is you calculate the diffusion coefficient. So alpha is given, delta t is given, delta x you have calculated 0.25. So from here you are finding the diffusion coefficient is 0.16. Okay, so for this kind of explicit methods, this coefficient d, its value is important. So there is one chapter in our course known as the stability analysis. Okay, so stability analysis of a numerical scheme. So you are using FTCS for this particular equation. For this equation, in this particular example, you are using FTCS. So FTCS is known as a differencing scheme. Now, this differencing scheme may be stable, may be unstable. It means that this differencing scheme may give you correct discretized equation or physically meaningless discretized equations. Okay, so if it is giving you physically meaningful discretized equations, it will converge, you will get your solutions. Otherwise it will give solutions that are meaningless, or it may not even give you solution. Okay, so for explicit scheme, always we have to satisfy some condition on stability, whether the numerical method that we are using for discretization, so that is a stable method or not. So to do that, we have to make certain checks. So this is for this kind of problems, diffusion problems, this is one parameter whose magnitude is important for checking. So this d is 0.16. Now we shall show at the end of this discussion that d equals to less than equals to 0.5 gives us correct result for such one-dimensional problems. Okay, so this is your first check that this d is less than 0.5. Okay, now for these explicit schemes, when you are using this formula, so if you want to find out the temperature at n plus 1th level, then you must know all the temperatures at nth level. So if you know this value at nth level, this value and this value, then only you can find out this value. So when you start your calculation, suppose this is an unsteady state problem, and I told you that in an unsteady state problem, there is always an initial condition. So initial condition and initial guess, these are in two different contexts. Initial guess is required for iterative method. When you are solving a matrix by iterative method, then you have to use one initial guess. But initial condition is the what is the value of the unknown in a transient problem at time equals to 0. So when you are, it can be time 0 or it can be any reference time. So at the start of the experiment or at the start of your calculation, what is the value of temperature at the unknown points? Those are specified. So that is the initial condition. So initial condition is compulsory for the unsteady state problems. So this is an unsteady state problems. We have to specify the initial condition. Okay. So initial condition means at n equals to 0. So when n equals to 0, then we say that it is our initial condition, and the first time step delta t, it starts from 0. So if we see that, if you tell that this is your initial condition, it means that this n will be 0. Okay, then if n is 0, then n will be 0 only, but n plus 1 will be second time level. So 0th time level, n plus 1 will be first time level, n plus 2 will be second time level, and so on. Difference between every time level, it is delta t. Okay, so this is clear. So n equals to 0, it means time is also 0. So at 0 time, when you are starting your experiment, that is your reference time. So that is your 0 time or 0 time level. So at that time, you specify your initial condition. Based on the initial condition, then you calculate your results at time delta t. Okay, at time delta t or the first time level. So if you want to calculate the solutions at the first time level, you must have to be provided with the initial data, initial condition. Initial condition means what is the value of the unknown at all the nodal points, non-boundary nodal points. So those must be given. So those initial conditions will be required when we solve this problem. So what we have done, we have taken 0 temperature. So 0 solution is known as a trivial solution. Okay. So for many problems, so 0 is a solution. And when we say that this is, when we are using 0 as an initial guess, we say that we are taking the trivial solution. It is found that in most of the problems, that solution of 0 as a starting point is a very good initial guess. So when you are using some heat transfer problem or fluid flow problem, you can start initializing your solutions with 0 at all the points. So what we have done that we have taken at all the unknown points like 2, 3 and 4, we have taken the temperature as 0 degree centigrade. Okay, so it means that now at n equals to 0 or at time t equals to 0, at every point, internal point, the temperature value, you know it, you have assigned it. Okay, now your initial, generally what happens that if you give some other student, if he takes a different temperature, suppose you are taking 0, somebody can take minus 10 degrees centigrade, or so here it is between 30 and 10, 100. So nobody will take minus 10. So somebody can take some temperature maybe between 30 and 100, or somebody can take little less than 30. Okay. So when you are taking some other solution, your final solution will not change. Okay. So I say that in general, it is not always, in general, different initial conditions for the same problem will not give you the different solutions, different final solutions. Whatever be your initial condition, in general, you will get the same solution. Every student will get the same solution if the discretization scheme is same. Okay, so initial condition is required to start your calculation. So your calculation may be lengthy, your calculation may not be taking much time. It depends on the initial condition, but different students, they are taking different initial conditions, but ultimately they will get the same solution. So this is important, this you have to remember. Okay, so it is not that everybody has to take 0, but taking 0 is better. Somebody can take 10 degrees centigrade also, so his results, his final results will not be different. Okay, so what is the explicit calculation step? You see, this is the trick. We do like this. At initial guess, time equals to 0, and iteration, this time level is 0. So there is nothing as iteration in explicit scheme. Okay, iteration is only in the matrix. Now here we are writing in this way, T2 TIN. Okay, so I is 2 for the second node, n is 0, so T20 is 0, T30 is 0, and T40 equals to 0. So if it is your 0th level, at the 0th time level, all these 3 temperatures, they are 0. Now you want to find the solution at the first time level where t equals to t or delta t. So t equals to delta t and n equals to 1. So n is 0, so n plus 1 will be 1. Okay. So here at the first time level, in using this formula, this is the generic formula. We write n equals to 0 and we write at node 2. Let us consider at the first node, second node. Okay. So I will be, wherever there is I, you put 2 there. Wherever there is n, you put 0 there. So this will be I. So t2, I is 2 and n was 0. So it is 0 plus 1. So this will be T2 0, I is 2 and N is 0, T2 0 plus, now D you have calculated 0.16, this D you are putting here 0.16, Ti plus 1, I plus 1 means T3, so T3 at 0th level minus 2 into Tin, I means 2, T2 0 plus Ti minus 1, I minus 1 means 2 minus 1, so T1 0, okay. Now this T20 you have taken as 0, initial guess you have taken T20 is 0, you are putting here 0, this is 0.16, so T30 you have taken here as 0, T T30 you have taken here as 0, T20 you have taken here as 0, but T10 this is coming from the boundary condition, okay. So this is T10, this is 30, so it is becoming 30 and you are getting the solution of T21 at 4.8 degrees centigrade, okay. So it means that this is 30 degrees centigrade at the first level of time, the transient problem, this temperature is coming as 4.8 degrees centigrade. Now similarly let us calculate temperatures at third and the fourth node. At the third node I equals to 3, n equals to 0. So T3 n plus 1 means T3 0 plus 1 equals to T3 0. This is the formula, this same formula we are using here. T3 0 is 0, we have taken T3 0 is 0, alpha is d is 0.16, okay. T40 is also 0, T30 is 0 and T20 is 0, so it is 0, okay. So it is coming that T21 is a non-zero quantity and T30 is a 0 value, okay. Then we consider the fourth node. When we calculate the fourth node, then we are putting in this formula and then we are finding T4 n plus 1 equals to T40, this formula, okay. Now there is one boundary node ahead of node 4. Because of that, this is getting a non-zero value. So T for 1, this is becoming non-zero. We are getting 16 degrees centigrade, okay. So it means that using the initial condition, you have calculated the temperatures at n plus 1th level or the first time level. So this has become 4.8 degrees centigrade. These are the boundary temperatures, first one and last one, boundary temperatures. This is 100. Now this has come to 4.8. This is 0 and this has come as most likely 16. I think it is 16. 16. So T4, it has come as 16. Now you have to calculate the temperature at the next level, at the second level. So what will happen? These three temperatures will change again. Okay. So this was 4.8. So only one step we have shown. It was 0. It was 16. Okay. So let us show at the second time level what is the value of T2. So we are doing it here. These things we are written here. So at the second level, n was 1. So T2, this is n equals to 0. This is n equals to 1. Okay. So in this case, what is happening? N equals to, it was 0. It was first level. This was now second level. N is 0. So this is the second level. N is 0 actually, always. In all these things, n is 0. So at the second level, T2 n plus 1, okay. T2 second level, we are getting T2 first level, we got 4.8. So we are trying to find out this temperature. This is this temperature, not this temperature. This is 1 minute. This is 2, this is 3, this is 4. So first we are showing for T2. So T2 at the second level equals to T2 at the first level plus other terms. This we have already calculated as 4.8. Okay. So we are putting it as 4 point, this is the formula 4.8. So alpha was, this d was 0.16, T3 1 it came as 0, T2 1 the same thing, it has come as 0.48, and T1 1, this is the boundary condition, Dirichlet type, it is not changing. So this is 30 degree centigrade. So this temperature at the second node at second time level, it is 8.04 degree centigrade, 8.064 degree centigrade. It means that this temperature was initialized as 0, then it became 4.8, now it became 8 point something. So at the third level, it will again change, fourth level it will change, fifth level it will change. So you can go up to 100th level or 1000th level. So when will you stop your calculation? Because you cannot go to n tending to infinity, okay? So in CFD, you are doing finite calculations. So this n will have a bound up to how much time level you will calculate. So you can calculate for 1000 time level, 100 time level. For a computer, calculating 1000 time level is less than, it will take less than 1 second actually. Okay, in 1 second it will give you a results. So 1000 or 10,000 does not matter. So the one condition is that you can give that, yes, I shall take the solutions as final solutions after 1000 time steps, and some other student he can tell that okay, 1000 time steps are not required, I shall take when solutions between these temperature, these levels and these levels, the maximum difference is less than 10 to the power minus 4. So that is also possible. Okay, so in that way also somebody can do the check, the convergence check of the results. So this is one incomplete example. So this you have to do actually. So I shall send you the note. So this is the concept that for explicit scheme, simple scheme, how will you do your calculation? Okay, so I have shown for one time step, and for the second time step, I have shown the partial calculation. And as I was telling that, this FTCS scheme is known as a conditionally stable scheme. Okay, so it is a parameter dependent scheme. It may give you correct solution or it may give you physically meaningless solution. So if you want to get physically meaningful solution, so you have to satisfy some stability condition. So for this particular problem, our stability condition is this diffusion coefficient d, this should be less than equals to half. Okay, so if it is happening less than equals to half, so your results will always converge. Okay, so it means that this d what we got at 0.16, so this is within this convergence limit. So if you continue with these calculations, okay, so your solutions will be correct. So this is one diffusions, this is one, this FTCS is one explicit scheme where we have this order of accuracy of delta t in time, first order accuracy in time, and second order accuracy in space. Okay, so we are getting in the FTCS scheme first order accuracy in space, first order accuracy in time, and second order accuracy in space. Now let us discuss the other available schemes, so that our desire is that we use the second order accuracy in time. So if we can use second order accuracy in time, we get better results. Okay. Now the thing is that one example which we are showing, that is known as the Richardson scheme. So Richardson scheme is giving us second order accuracy in time. So this FTCS scheme, this gives first order accuracy in time. Okay, so order of delta t. And when you are going for the Richardson scheme, we get central difference in space and central difference in time, and it gives us second order accuracy in time and second order accuracy in space. Okay, but this scheme does not work. This scheme does not give us physically meaningful results. Whatever the results it gives, those results are incorrect. Those results we cannot use. Okay, so it means that this Richardson scheme we don't use in our real applications. Okay, so this is the Richardson scheme for this particular equation. So we have to use central difference in time and central difference in space. So we shall discretize this equation at the ith node at the nth time level. Okay, so when you are going for the central differencing for this special term, you are discretizing it at the same point, ith point, but you are using n plus 1th level because this is nth level. So for central differencing, you will use n plus 1th level and n minus 1th level. Okay, so this is the central differencing in time. Tin plus 1 minus Tin minus 1 by 2 delta t. And in the right hand side, you are having simple explicit part. Okay, so this is the central difference approximation of the second derivative. And then this is the central difference approximation of the second derivative, and this is computed at the nth time level. So if you see, if you look into this expression, we have three different time levels, n plus 1, n, and n minus 1. So n plus 1 is unknown, n is the known, and n minus 1 is known. It means that in this particular equation, there is only one unknown. This is the only unknown term. Okay, so these terms are already known. This is known even before that. So you have only one unknown from one equation. So you can find out this temperature. But whatever the solutions you are getting for this temperature, that is physically meaningless. So you are getting wrong solutions. Okay, so order of accuracy is times accuracy is 2, second order accuracy. So we generally want to use the second order accuracy in time. So it means that Richardson scheme, this is only for the purpose of learning. It has no practical implementation. So Richardson scheme is not used in our real calculations. Okay. So this is not used. So this is only for learning that what are the schemes that do not work for the calculations. Okay. So in the chapter of stability analysis, we shall show that why it fails actually, that why it cannot satisfy the stability conditions. So the third scheme and the last scheme under this explicit scheme of this heat diffusion equation, this is known as the Duford-Frankel scheme. So this Richardson scheme or Duford-Frankel scheme, these are three-level schemes. There are three levels in time, n plus 1, n, and n minus 1. So Duford-Frankel scheme, this is also a third level scheme, and this is second order accurate in time, and this is unconditionally stable. It means that you can calculate and you can get correct solutions when you are discretizing your marching problem using the Duford-Frankel scheme. Okay, and you get the second order accuracy in time. So for this particular scheme, we get this kind of accuracy. So this you must note the difference. Okay, so second order accuracy in time, second order accuracy in space, and time scale by space scale to the power 2. This is also coming in the order of accuracy. So this will come because of this term. Okay, this last portion. So here, if you see the Duford-Frankel scheme, what we do? This unsteady term, this unsteady term or transient term, this is discretized by central difference. So this is central differencing in time and central differencing in space, but we modify the central term. Okay, so this is, you see that in a Richardson scheme, whatever you are getting, you are using central differencing in space and central differencing in time. Same thing you are doing in the Duford-Frankel scheme also. You are using central difference in time and you are using central difference in space. Only difference is that the middle term, the point of interest is node I. At this particular point, you are invoking n plus 1th level and n minus 1th level. So you are taking that Tin is an average of Ti at n plus 1 and Ti at n minus 1 time levels. So this should have been Tin. Here you see here we have taken it as Tin. Okay. So here there is a modification. So this Richardson scheme becomes Duford-Frankel scheme when Tin is an average of these two temperatures. Okay. So Tin plus 1 and Tin minus 1. Just because by this small modification we get unconditionally stable. So you can use this Duford-Frankel scheme for your calculations. Okay, so this order of accuracy you should remember that this is order of delta t to the power 2, second order accuracy in time, and second order accuracy is generally required. Okay, so this is, there are this only these three differencing schemes. This is for the explicit formulation. Okay, for this heat diffusion equation. And then the last portion in today's lecture is this introduction to this implicit scheme for this marching problem. So you already know that these marching problems, they can be solved by explicit scheme or by implicit scheme. Okay, but these equilibrium problems, they can be solved only by marching, only by these equilibrium problems can be solved only by implicit schemes. So whatever the three cases we have shown, FTCS, Richardson scheme, and the Dufort-Frankel scheme, these are for the explicit scheme. We have one equation, one unknown. So if you look into this equation, n plus 1 terms are the only unknown terms, n terms are the known terms, and n minus 1 terms are the known terms. Okay, so what we do, when we simplify this equation, the terms with tin plus 1 we keep to the left hand side, and remaining all terms we shift to the right hand side. Okay, and then we have the situation of one equation and one unknown, and we can solve it. So next we introduce this implicit schemes for the marching problems. So the first implicit scheme that we discuss, that is the BTCS scheme, or backward in time and central in space. So this we have already discussed. So this is also known as the backward Euler scheme or the Lassonine scheme. Okay. So this is first order accurate in time and first order and second order accurate in space. So this is our governing equation. This governing equation is discretized at the ith nodal point at n plus 1th time level. Okay, you know this expression already. Okay, you know that when we are using implicit scheme, we get a matrix. For one-dimensional problem, we always get a tridiagonal matrix, and the coefficient of these unknown terms, nodal values, they are giving us the diagonals of the matrix. The point at which we are writing this equation, its coefficient will give us the main diagonal coefficient. Okay, so this equation, we can see that in implicit scheme we have many unknowns. We have three unknowns: terms with n plus 1, these are the unknown terms, and terms with n, these are the known terms. Okay, so it means that in one equation you have more than one unknown, but in explicit scheme, in every explicit expressions, we have one equation, only one unknown. So this is a big difference that you must solve the matrix problem. Okay, so this, after you simplify and we define d equals to alpha delta t by delta x whole square, then you simplify here, then all the unknown terms you shift to the left hand side and the known terms you shift to the right hand side. This is the final appearance of this matrix. So this minus 2d plus 1, this becomes your diagonal term. So if you look into this expression, so we have three diagonals. So in one diagonal, sub-diagonal will be d, main diagonal will be minus 2d plus 1, and super diagonal will be d. So you are getting three diagonals, then we have to use the Thomas algorithm. Okay, then when we are using Thomas algorithm repeatedly, then at the nth level and n plus 1th level, we are showing all the four temperatures. Okay, these three temperatures as unknown, and then one temperature as a known temperature. So this particular temperature, this is the known temperature in the right hand side, this is here. So this is this grid stencil or grid structure for this implicit scheme, this simple implicit scheme or the Euler scheme. So when we are talking about the explicit scheme, we have to satisfy always some condition, okay, some stability condition. So if we cannot satisfy the stability condition, we get meaningless results, or even sometimes we may not get result. So it means that, suppose for this particular example, you have to satisfy that is grid Fourier number. This is also known as the diffusion coefficient or the grid Fourier number. In one dimension, it should be less than equals to 0.5. So this less than equals to 0.5, there can be infinite combinations by which you can satisfy this condition. Okay, so you can increase your delta t, you can decrease your delta t. So whatever the way, suppose you decrease your delta t, increase your delta x, then whatever be the value, alpha may be constant. So from here you can control your delta t size. So in explicit scheme, we just mentioned that the delta t should not be large. So the value of delta t, it should be selected very carefully so that the product becomes always less than equals to half. So this is obtained, this is generally attained by using small values of delta t. So suppose the particular problem, we have taken delta t as 0.01. So this is a very small value of this time step size. So this kind of time step size if you use, then you are getting correct solutions. Okay, so it means that
Explicit schemes are conditionally stable and sometimes they can be unconditionally stable. So Dufort Frankel scheme is unconditionally stable. And when you are going for the implicit scheme, suppose when you are going for this BTCS scheme, BTCS scheme is unconditionally stable. So when it is unconditionally stable, it means that you need not satisfy this kind of any constraint for your discretization. So it means that for explicit scheme, there will be some constraint always. For implicit scheme, there is no constraint. So you don't have any restriction like this. Okay. So it means that you can use practically any time step size for the implicit scheme. So theoretically it can be any time step size, but practically we don't use any time step size. So what we do that? We just use a small time step size. Okay. Means a big time step size. So what we can do that? When we are going for the explicit scheme, it means when we are going for the implicit scheme, we use time step size that is bigger than that used in the explicit scheme. So I want to say that for this example problem, for this explicit scheme, our delta t was 0.01. Okay. So for implicit scheme, you can use 0.05, or you can even use zero point 0.1. Okay. So you can use zero point 0.1 also, and you will get correct results. So it means that in implicit scheme you can take bigger time step size, but in explicit scheme your time step size must be small, otherwise your method will collapse, method will not work. Okay. So this is all about. So remaining regarding this remaining implicit scheme, we have this Crank-Nicholson scheme, this ADI scheme in 3 dimensions. The ADI scheme yesterday we have discussed in 2 dimensions. Okay, and then there are some special topics in the finite difference method. Then we have some topics, the stream function vorticity formulation, finite volume method, and then finally we go for the Navier-Stokes solver. Okay, so we end here today. I shall send this note later. Okay, thank you.